tree is a data structure which we are going to use to store the data. Like any other data structure like set, map, we are going to store data in a particular format, and that format is a parent-child format. So tree is a data structure which is used to arrange data in a parent-child format. Now arranging data in parent-child format will create a hierarchical structure. You see this circle? We are going to call this circle as a node. Now every single node will have data stored. Now in this case, it's just an integer number. It is 7. It could have been a string as well. Like you can have a node where there is a string like OK or hello world. So a node stores the data. Also look at this line. It connects two different nodes. You have a node with data 7 and you have a node with data 5. We call this particular line as edge. As you can see, data is stored in a particular format, and that format is a parent-child format. To understand this parent-child format, let me define some terminologies for you. That will make much more sense for you to understand what exactly this parent-child format is. So what is a parent? A node that is an immediate predecessor is called as parent. For example, 7 is parent to 4. Why? Because 7 is an immediate predecessor for 4. Similarly, 7 is immediate predecessor for 5. So, 7 is a parent of 5 and 4. Similarly, this node 50 is a parent of node 12, node with data 13, node with data 20. Makes sense, right? So, a parent is an immediate predecessor. Likewise, the immediate successor is going to be a child. For 7, 4 is child, 5 is also a child. For 4, 15 is a child and 50 is also a child. So if we look at the data that we are going to store, of course we are not going to store in this format in memory. Computer doesn't understand this line and these circles. This is for us to understand. Whenever I say a tree, you are going to visualize it in this format only. So we learn what node is, we learn what edge is, we learn what data is. See, we are calling this as a tree, correct? We already defined what parent and child is. You see this particular node with data 7. If you observe carefully, there is no parent to it, correct? That's why this node is called as a root node. The topmost node with no parent is called as root node. Likewise, look at these yellow nodes. None of them has a children. Like 5 has 2 children, 2 and 3. But there are no children to node 2 or node 3. So all these nodes with no children are called as leaf nodes. Now there is something called as ancestor and descendant. Any node on the path from root to that particular node is called as an ancestor. For example, if I ask you, what is an ancestor of 13? Node 13. So let's start from the root node and travel to node 13. So this will be the path you will be taking, right? Path consists of multiple edges. So these are the edges that we are traveling ultimately. And we travel from 7 to 4 to 50 to 13. So all these nodes 7, 4, 50 are going to be the ancestors of 13. Similarly, for 3 also, we have 5 and 7 as an ancestor because you need to travel like this to reach 3. So what are the descendants? It's very simple. If node A is a parent of node B, then node B is going to be a descendant of node A. That means for this 4, you have 15, 50, 12, 13 and 20. All these are going to be descendant of 4. Similarly, all these are going to be descendant of 7 because 7 is an ancestor to all of them. Now if you look at this particular node 4, you have 15, 50, 12, 13 and 20 as descendants. If you look at this particular section highlighted as a red, you see that this is also a tree with root as 4, which is a part of bigger tree. So this is our original tree. But if you collect a node and all its descendant, then it also forms a tree. That tree is a part of original tree and this is called as subtree. Similarly, this is also a subtree. Node and all its descendant make a subtree. After that, we have something called as level or depth. Level or depth is number of edges that you are going to travel to reach that particular node. So for node 7, it's going to be 0 because you will not be traveling any edge. For node 5 and 4, it's going to be 1. Why? Because this is the edge that you will be taking to reach them. So number of edges that you need to travel is exactly 1. For 20, level is going to be 3. Why? Because these are the 3 edges that you will be traveling to reach node 20. So level or depth is nothing but number of edges that you need to travel to reach that particular node from the root node. Remember, from root node. You are going to take 3 edges to reach node 20 from the root node. What is diameter of the tree? Well, it's the length of longest path between any two nodes in a tree. See, you select this node 3 and 15. What is the path between these two nodes? Well, you need to travel 1 edge, 2 edge, 3 and then 4. So total number of nodes that you are going to visit from traveling from 3 to 15 are going to be 5, right? You start from here, you visit 5, then you visit 7, then you visit 4, then you visit 15. So total 5 nodes you are traveling. By selecting intellectually, can I travel more number of nodes? And the answer is yes. You can select 3 and 13. Well, you will be traveling something like this. So the total number of nodes that you will be traveling are 1, 2, 3, 4, 5 and 6. Correct? But we can select 2 and 12 as well. You will be traveling 6 nodes in this case as well. But that's not the point. It's not about start or the end point. It's all about the maximum number of nodes that you are going to take. That's what diameter is. No matter what you select 2 and 20. The total number of nodes that you are going to travel are 6. You cannot travel more than 6 nodes in this particular tree, correct? So diameter is the maximum distance between any two nodes. So what node you select doesn't matter. You can select 2 and 20, you can select 3 and 12, or you can select 3 and 13. It doesn't matter. Now we have already seen that tree is a data structure that has some data and that has children. A node can have multiple children, correct? But there is a special case. If there exists a tree where you can have at most 2 children, then that tree is called as binary tree. And this is a special case. That's why I am highlighting here. So ultimately every single node is going to store the data. It's going to store the left child information and right child information, correct? So you have a node that is going to store the data. Let's say 7 is the value that it has stored. It also needs to store the left and right child. Either we are going to store the address or we should know the address. If I want to store a binary tree into an array, then that would be much more easy. Let's say array I is going to represent data at node I. Correct? And I into 2 plus 1 is going to be my left child, and I into 2 plus 2 is going to be my right child. So array of I into 2 plus 1 is going to store the data at I into 2 plus 1. Makes sense, right? By defining this particular rule, I managed to store the entire tree or specifically binary tree into an array. Now there are furthermore classifications to this binary tree. Well, we are going to deep dive this when we actually talk about the problem, or we talk about this in a separate video. But just to go through it, a full binary tree is every single node has either 0 or 2 children. So there is no node where you have exact one child. That is not the case. In full binary tree, you will either have 0 or 2 children. Then we have a complete binary tree where all levels are fully filled except the last one. Let me give you an example, you will understand much better. Let's say you have a tree like this. Correct? Now the problem with this tree is not all the levels are completely filled. Let me give you an example. So this is the level and you have one node. Of course you will have one node. It's going to be a root node. No problem. Then you have this particular level. Correct? This is level 1. Remember, level is number of edges that you need to travel. Now on the level 1 you can have at most 2 children, correct? Because we are talking about the binary tree. And we have 2 children. Okay, that's good. Then let's go to the level 2. Now on level 2, you only have one child. Either you should have this left child, you should have this right child, and you should have this right child as well. So total children should have been 4. But we only have one child here. Correct? This one child is already present. On level 2, we should have 4 children, but we only have one child. That means level 2 is not completely filled. But look at this. All levels should be fully filled except the last one. So this level is not fully filled. And the problem is this is not the last level. Last level is the next level, level 3. So this is not a complete binary tree. But if I just remove this particular node, now this can be a complete binary tree. Why? Because level 0 is completely filled, level 1 is completely filled, level 2 is not completely filled, but this is the last level, right? So it doesn't matter because we want all the levels to be fully filled except the last one. Then we have balanced binary tree, and it says that height difference between left and right subtree should be minimum. Here, height difference between left and right subtrees, this is the subtree, this is the subtree, height is here 2 and height is here 1. So difference is going to be 1 for this particular node. We will compute for this node as well. Here height is 1 and here we don't have nodes, so height is 0. So the height difference between left and right subtree should be minimum. We are going to deep dive this balanced binary tree later on as well, so I am not going to put much emphasis on this here. So let's move forward. Now this is a generic tree, and that's what we usually mean by a tree. So every single node will have a data and it will have an information about all its children, either their address or something like that. Let's look at some properties. See, in a tree, let's say you have n number of nodes, correct? Now tree has a property that it doesn't have any type of cycle, and you can travel from any node to any other node. That directly gives you that there should be exactly n-1 edges. For n nodes, you should have exactly n-1 edges. Imagine if you have n edges. That means it's going to create a cycle somewhere. And imagine you have n-2 edges. That means all nodes are not reachable from every other node. But the tree is a special data structure where every single node can be visited from any other node. You can travel by the edges to any other node. Also, there are no cycles. So this gives us the total number of edges as n-1. So if there are n nodes, then there has to be n-1 edges. We have already seen what depth of the node is. It's nothing but the level. We have already seen the number of edges that you are going to travel from the root to a given node is called as the depth of the node. So the length of path from the root node to a given node is called as depth of the node. We have already seen it. After that, we have something called as degree. Now degree is number of children that a node has. For example, now this particular node has 3 children. So degree of this node is going to be 3. So whatever is the maximum degree of a node, it's going to be ultimately degree of that tree. The degree of tree we are not going to use much, but degree of node we are going to use it. There are a lot of applications of degree of node that we will cover later on. Now let's focus on representation. See, why do we need to focus on representation? See, this is what we are calling it as a tree, correct? But all these nodes, these circles and these lines and these numbers are not identified by computer. So you need a way to store all this information, data and its children. All this information you need to find a way to store into the memory of a machine, correct? And that's why it's very important to look at how exactly are we going to code this tree. So let's start from the binary tree, which is very easy. We have already seen it. A node will have information about the data and it will have an information about left child and right child address. We are going to store that into a pointer. Simple, correct? So you have a node, it has an information about the data and it has information about the pointer of left and right child. Simple as that, correct? As this is just a binary tree, we need left and right child information, as you can have at max 2 children. Simple. Now using array, we have already seen it. Array I will have data at node I. So array I is going to store the data at node I. And I into 2 plus 1 will have left child information and I into 2 plus 2 will have right child information. Very simple, correct? So if I just go here, you will have an array. So at index 0, you have 7. Now 0 into 2 plus 1, it's going to be 1. So left child information is going to be at index 1. So left child is 5. Okay. Now 0 into 2 plus 2, this is going to be right child information. And this is 2, correct? 0 into 2 plus 2 is 2. So at index 2, you have 4. This is the right child information. After that, 1 into 2 plus 1. This is left child information of 5. This is going to be 3. So at index 3, you will have value 2. See, this is value 2, right? Data 2. We are going to store it here. For this 5, we have I as 1. I into 2 plus 1 is going to be left child. So 1 into 2 plus 1 is 3. So at index 3, you have node 2. Similarly, you can fill the entire array. So at index 4, you will have this 3. This 3 is going to go to index 4. After that, you have index 5, which is going to be 2 into 2 plus 1, a left child of this particular node. So it will have data as 15. The important thing is here that, let's say your I is 3. Now 3 into 2 plus 1 is going to be 7. So on index 7, you will store left child information of node 2. But there is no left child to this 2, right? So you can store here -1 or 0. Anything will be fine because 2 doesn't have any left child. In binary tree, we had a data. That's good. And we have information about left child and right child pointer. Okay. But now we can have multiple children for a generic tree. That's why we are storing all the addresses of children into a vector of nodes. Now here I have used class. You can use class or struct, no problem. The concept should be clear. Every single node will have the information about the data and all its children. That's how we are going to store the tree. Look at the tree, right? See, this 7 we have. This 7 is a data of this particular node. And this node should have information about its children. That's how we are ultimately going to end up in parent-child format data structure. And this parent-child format data structure is called as tree. So everything comes back, right? Similarly, you can store the information in this format as well. And this is the most commonly used format. Let's say the maximum number of nodes are 10 to the power 5. And they will define this in problem statement itself, that maximum number of nodes that you can have are going to be some x number. Usually it is 10 to the power 5. So for 50, you have 12, 13, 20 and 4 are its adjacent, right? Look at this. For 50, you have 12, 13, 20. All its children, we are going to store the information of the children. But also we are storing the information of the parent as well in this particular representation. Similarly, for 15, we will store only 4. For 5, we will store 7, 3 and 12. And this is the most commonly used format in competitive programming to store a tree. So generally, in a CP problem, you will have input like this. The first line will have value of n, total number of nodes that are going to be there in a tree. After that, you will have n-1 lines with A space B. That means A is connected to B. And this is going to be our tree. First, we will take the total number of nodes that we have. After that, we have n-1 edges, U and V. Here I am doing A and B. Here I am taking those values into U and V. No problem. Then we are going to define edge between U and V. Remember, when we store the tree in this format, we store all its adjacents. So when there is a edge between U and V, both of them are going to be adjacent to each other. Let me just show it to you how exactly it will look like. So G of 7 will have 5 and 4. Correct? Then we have G of 5. It will have 7, 2 and 3. All its adjacent nodes. I hope that my point is clear. You can see G of 12 will have only 50. Similarly, 13 and 20 will also have only 15 because 50 is adjacent to 13, 20, 12 and 4. This is the most commonly used format